So our today's topic is about magnetic resonance imaging. Right? So if you're taking chemistry A level, you have learned about the CNMR. Right? It's the same concept. So it's the same thing actually. They are using the same principle. Okay. So now we start with the principle of the nuclear magnetic resonance. So at first, right, we have a random position of the magnet. So the N and south are randomly placed. So you learn already in chemistry, right? Inside our body, what do we have? We have hydrogen atoms, right? And hydrogen atoms as well. Hydrogen atom has spin, right? So remember that term? So the one that you look on the board, like the board right here, that's our hydrogen atoms, and it has a spin. This one is before the electromagnet is applied. This one is before electromagnet applied. So the spinner, it behaves like a tiny magnet. Now, we apply the electromagnet. So you know that when the patient lies inside the machine, the electromagnet is switched on. Right? So now you apply the electromagnet already. So what happened is, this one is north, this is south. Right? So you will see the magnet, the tiny magnet, the spin is being aligned, but not all of them. So most of them will be aligned, having a south facing the north. But few of them will go against that. So most of them will follow the electromagnetic field that you apply. Most of them, but few of them, right, will go against that. Just now someone chat me. Any questions until here that you like to ask?
No, sir.
My voice for others clear not? Because at Malati first it's not very clear.
Yeah, clear for me, sir.
Okay. Okay. Now we have to discuss about what do we mean by the precision. So now let's say this is a magnetic field applied. So your magnetic field applied just now, heading from north to south, right? So go from top to bottom, right? Understand? This one is our magnet just now. So your magnet is aligned. Most of them is aligned along the field, right? Only few of them resist the field. But then on the other hand, when he is aligned with the field, the magnet also spins. Your proton or your hydrogen atoms or the tiny magnet also spin. That is the direction of the spinning. That's why we say hydrogen atom has a spin. So in chemistry, we say hydrogen atom has a spin, right? Why we say hydrogen atom has a spin? Because the behavior of the hydrogen atoms, when you apply a electromagnet, some of them will resist it, but most of them will follow it, right? Once they follow the electromagnet already, or even though they resist it, they always spin. So the hydrogen atoms always spin. That's why we say the hydrogen atoms has a spin. Understand until here? This spinning process the magnetic axis rotates around the direction of the external field. This spinning or this rotation or gyration is known as precession. Do you understand until here? I will share the video, but if you want to take a picture of the board, you can do so. Okay, I clear the board. Now I continue again. Now, if something is spinning, then we say they have an angular velocity. Something spinning, we say have angular velocity. Understand? So in this case, the angular velocity or the angular frequency of the precessions, right, is known as Larmor frequency. So Larmor frequency is the angular velocity or the angular frequency of the spinning processes of the precession. Understand? Larmor frequency, omega, right? So remember, omega O, the Larmor frequency, is given by a formula equals to gamma. The symbol is gamma, I mean, gamma times a BO. So you know BO is a magnetic field density. So the BO at here that we use is 1.5 Tesla. Usually, this one is very strong already. Then the gamma has a value of 2.68 times 10 to the power of 8 radian per second per Tesla. Radian per second plus Tesla. Then by using this, you will be able to find the omega O. You will be able to find the omega O. Once you get the omega O, you will be able to find the frequency. The frequency O. I mean the frequency of that omega. You understand here? Now, if you get the answer later, if you do this process over, the frequency that you will get is around 64 megahertz. And if you check this amount, if you go to the electromagnetic wave discussion, this amount lies in the radio wave. That's why in chemistry, when you learn, we say when you do this process, right, we say the electromagnetic wave that we use is the radio wave, right? If you remember. So in using the MRI machine, right, we need a strong magnet, and also we need to use a electromagnetic wave. And the electromagnetic wave that we use, right, lies in the range of radio wave. How can we tell that? So if you count it with this, right, you will see that it lies on the range of the radio magnetic wave. So far, do you have questions until here? No. If no, then we continue again, yeah? How to get resonance? To get resonance means the frequency that we give have to be the same with what? The natural frequency, right? So we have to recall resonance. Need a system with a natural frequency of the vibrations, right? So right here, the Larmor frequency is a natural frequency. So when this happens, it will stimulate energy of the same frequency. I mean, in resonance, right? If you give a frequency which is the same with the natural frequency, you will cause the object to resound, right, with a greater amplitude. So it will produce a greater amount of energy.
Just now you say Larmor frequency is the natural frequency.
Yeah. So in the MRI, the protons precessing about the strong external magnetic field and it is also being exposed to the loss of radio electromagnetic wave, right? RF wave, radio frequency wave, whose frequency is equals to the Larmor frequency. So just now I told you, right, when you use this MRI, you allow the patient to lies inside the machine already. You switch on the electromagnet, right? And at the same time, you should apply electromagnetic wave, which is the radio wave. Why radio wave? Because the radio wave frequency is the same with the Larmor frequency that you have calculated here. Why should it be the same? Because we want the resonance process to happen. So if you don't use the same frequency with the Larmor frequency, then there is no resonance process. Then the next question is, after the resonance process happen, what do we expect? Why we need to have a resonance process? That's what we are going to discuss next. Any questions until here? Okay, then we continue again. Okay, so each of the protons will absorb what? So you apply a frequency, which is the same with the natural frequency, right? So they will absorb energy, right? And the resonance will happen. So each proton will absorb the photon of the RF energy and flips up into higher energy state. So when you do this, right, you are giving the proton an energy to resist the magnetic field. Just like I told you earlier, most of the cases, the protons will go along the field. That's the normal things, right? Because you have a very strong magnetic field. Of course, a tiny magnet should go along with that field. Only some the cases extraordinary, they against that. But then when you apply the electromagnetic wave in the range of the radio wave frequency, the protons that at first go along with the field will have the ability to go against the field. They have the energy to go against the field. How do they get the energy from? From the resonance process. Because the resonance process will cause them to have a greater amplitude, right? To have a greater spinning. So they will be able to resist the stronger field. But that one only can happen if it's exposed to the electromagnetic wave, the radio frequency wave. If you switch it off, will that happen again? No. So that's the next one. If the RF wave are switched off, the protons gradually relax into their lower energy state by releasing energy. Also in the RF wave form. This is known as relaxation. So when they do this relaxation, sir, you will be able to note the time. Time taken during the relaxation process will tell us the nature of the hydrogen atom or the environment of the hydrogen atom. How long does it take to come to rest will tell you if it's a healthy tissue or not a healthy tissue. Understand why you need to undergo resonance? Because by allowing it to undergo resonance, by allowing it to go against a stronger field, you have a chance, when you switch it off, right, you have a chance for it to come to a relaxation state. So during this relaxation state, we need to note down the time taken. How long does it take so you can identify if it's a strong tissue or not? Any question until here?
What's RF again?
Radio frequency.
Okay.
It's actually radio waves.
Sir, if the time longer means the tissue stronger, yes, sir.
This one, after this, I give you the time. They already have a certain value, see?
Oh,
This one is what? Any question again?
no,
Should I take a picture of the board before I clear it out? So I can clear the board now. Okay. This one, yeah? Water and watery tissues have relaxation times of several seconds. This is me right now. Fatty tissue have a several hundred milliseconds.
Okay, sir. Nice joke, sir.
Cancerous tissues have an intermediate, so directly relax.
Cancerous tissue is me.
So if it's cancerous tissue, right, it will come to rest immediately. Any questions until here? No.
Is this the one in chem, like the round thingy yang go up and go down one, yes, sir?
Yeah, but then yeah, in chemistry, I need to tell you in short, right? Last time I tell you the resonance can happen. So in physics, we learn totally how does the resonance happen, why the resonance need to happen. Sorry, this one is important part. Right? So just to summarize, just now I mentioned, you need a large superconducting magnet, right, to produce a external magnetic field, right? Then we need a RF coil to produce a RF pulse, right, into the body, right? Because you need to use this at the same time also, right? And then when your body tissue come to a relaxing state, it will emit energy, right? It will emit energy. Energy is equal to H times frequency, right? And the frequency is also in the RF wave, right? Also in that range, right? So the RF coil also will detect the signal emitted during the relaxation stages, right? Still okay until here. Then this is what is more important again. If I explain to you, That's when I thought first, I'll explain to you. First, pay attention to the spelling of the Lamor. I think I missed up just now. Lamor is the correct. This is the correct way. Okay. I think point ABC is supposed to be clear already. Anyone want to ask question point ABC before I go with part D? For part D, right, the consideration is like this. Imagine, right? Imagine if you do this process, right? Let's say you use this kind of wave, right? And then everything have the same value. All of the protons right, undergo the resonance at the same time. We'll be able to tell the protons or the hydrogen atoms or the cell is coming from the head, coming from the body, coming from the leg or the stomach. We'll be able to tell that. No, it will take a very huge memory to analyze those results. Right? So the idea that they suggest is, so when I say the radio wave always have a frequency, right? From this value to this value, right? Okay, we know the radio wave frequency have to be around like just now 64 megahertz. Maybe we can adjust the decimal. Use a wave in that frequency, but then along the function body, right? Don't make all of the frequency the same. For the head part, for the stomach part, or the leg, or the stomach, or the intestine, you make it vary a bit. Just a bit different. Why? So when they undergo the relaxation process, right, they don't emit the wave at the same time. So you have a chance to analyze, right? This is coming from this part, this is coming from this part. Right? That's why you have to set the frequency to be slightly different. But most of the times, it's very difficult for us to set the frequency to have a different value. Actually, you can do so. If you remember last time, I say it would be difficult for us to change the radio wave range because the device will be expensive. Right? So what the scientists do is they change the magnetic field. You have two options because when you pay attention to the formula that I write, when you find the Lamor frequency, the formula depends on the magnetic field also, right? The B, right? So you can adjust the B and not only the radio wave. So it's easier for us to adjust the B. That's why at point D here, they suggest you to use a gradient coils. They name it as a gradient coils. The purpose is to add the extra magnetic field. So if you add the extra magnetic field, the frequency will be different for each part of the body. So we have enough time to track, or it will be easier for us to track. So again, it is okay if you want to change the radio wave. Let's say you don't want to change the magnetic field, right? You want to change the radio wave, that is okay. There's also one of the way to do. But then practically, no one do that because you need to provide several sources of radio wave, right? is much more difficult. So the one that is easier is, it's easier for them to find electromagnet. Making magnet is easier, right? Rather than you buy a machine that produces a radio wave. That's why at part D, if you read the textbook, they suggest you to change the magnetic field rather than they change the radio wave for each part of the body. Any question?
Just now you say you vary the frequency for different parts of the body so that they don't emit what? I don't catch that now. Not here.
If you vary the frequency, right, means they will relax at different time. Not whole of the patient body relax at the same time. If they relax at the same time, it will be confusing. Understand?
Okay. Thank you, sir.
Okay. Any other questions again? No? So you just clear the board. I'm going to take picture first. Okay, I clear the board already.